Hello guys. Okay, last week we had the introduction of this course and we went through some of these basic concepts and we introduced the idea of probability and we also have the idea of the conditional probability here. Okay, so that if we have two events, okay, the probability of B given A is defined as the follows. Is that relation here? Okay, that is to say, the probability of some event B may depend on the result of event A, may depend on whether A has occurred or not. So imagine as things happens as time goes on, the probability of certain event B may change as other things happen. So given by this expression here, and we had the very important concept of independence of events. So for instance, if I'm throwing a coin and I'm throwing a die at the same time, you wouldn't expect whether I get a head or a tail from my coin has anything to do with what score I'll be getting from a die. So they are called independent events. In which case, whether A happens or not has nothing to do with the probability of B. It doesn't affect, so they have the same thing, and therefore we have the basic relation of probability of A and B both occur to be the product of the two. Probability of A times the probability of B. That is the basic concept of conditional probability. And we at the end of last time we talked about then the very important the idea of the total probability. Suppose that we've got an event A there, and I would like to know the probability of it. And suppose that our sample space is divided into a number of smaller subsets, B1, B2, B3, all the way to Bn, if you have a lot of them. Okay, then the probability of A, if I let me show you with the picture again, the probability of A, this blue region here, the region surrounded by the blue line there, okay, would like to find the probability of A is really given by all of these green bits, green shaded regions, where it's just they're just the different intersections of A together with the B1s, B2, B3 and all that. I'm adding the lot together so that we have the sum of the lot, and it's going to be given by the conditional probability of these guys. Probabilities of A given B1, probabilities of A given B2, and all that. This is what we call the total probabilities. The thing is, imagine this. I've got a deck of playing cards. Imagine I've got a deck of playing cards, 52 cards, the usual thing, deck of playing cards, 52 cards. Suppose that we're playing a game and you win. Okay, you just take one card from my deck. If you get a 3 of hearts, for instance, if you get a 3 of hearts, okay, then you win. Okay, I'm taking my deck of cards and then pass it around. I'm going around and the classroom and ask each one of you to pick one. Okay, of course, if you take one, if it is and then you're not returning my card, you take my card there, so I've got 51 cards left. If you get one, or if you get a 3, or if you not get a 3, then I'll just move on to the next guy. Okay, suppose that you and your mate will ask, okay, I've got 52 cards and you and your friend are here. Would you prefer to draw the card first, or would you prefer to go second? Or does that make any difference at all? Okay, you normally would think, okay, I've got 52 cards, it is kind of unlikely that someone would pick out the 3 of hearts in the first go. So but so you would prefer to go second. Normally, that's what people would think. Prefer to go second so that your friend next to you would pick out the wrong card, and then you've got only 51 cards left. So it makes it more likely to get the winning card, the three of hearts. Yeah. Or I don't know, maybe you would think something different. Maybe you prefer to go first. Pick the just in case my friend would get the winning card immediately. So I'll go first so that I have more of the chance. Maybe there's a more of the chance after all. Which would you prefer? We can actually work that out using probabilities here. You can imagine if you pick first card, if A is first card, win. Okay. If I write down the events like to pick the first card and then win, then the probability of A is simply 1/52. There's only one three of hearts in my deck of 52 cards. If you pick the first card and win, there's only 1 from 52 of the. And if I let the second card, okay. If you pick second, okay, pick first and sorry, I have to change it a little. I will say pick first and win. First and win. And pick second and win. Okay. If I define another event here, like event B, like picking the card second. Okay, you don't go first. Your friend goes first. Okay, and then you win. What's the probability of that? What is the probability of that? Well, and now we've just discussed that. Well, it kind of depends on whether your friend would get a card first. You see, so we have this as a total probabilities. You either have your friend, okay. You either have a friend picking out the winning card. Okay, sorry, I'll do it in full. You either have this or this. Either your card, your friend get a winning card, win, not win. Okay, either your friend pick the winning card or he doesn't. Yeah. So we can write it down as the conditional probabilities as well, the probability of you winning given that he has already won. According to our formula, that's what we would have, the probability, and then we have the second term as the probability of you winning given that he doesn't win. Okay? But the thing is, we know that there's 1/52 of the chance for your friend if you go second. For your friend who picks first to win the card and to pick the winning card, 1/52. But if he wins, there's no way you can win. There's only one card. If he wins, there's no way you can win. On the other hand, if he doesn't win, so he's picked 51 out of 52. He picked the wrong card, so not the one that we were looking for, the three of hearts. Then you have 51 cards left, and then you pick the right one. Of course, the first term is just 0, but the start one that gives you 1/52. Exactly the same as before. So according to our calculation, it doesn't really matter whether you go first or go second. It doesn't really matter whether you go first or go second. Okay? In fact, it wouldn't matter if you say like if I change the question as if you pick out a 3, then you win. Okay, not just the 3 of hearts. If you just pick out a 3, so you got four cards, 4 winning cards here. Okay, would it matter? Would it matter if I change that to, let me change my color as well. If I change that to 4/52, okay, so that this guy would be, this calculation would be, okay, there's 4/52, sorry, actually, so there's a 4/52 of the chance of me picking out the winning card, and then you've still got 3 from 51 to win. On the other hand, if you pick the wrong card in the first place, so you've got 48 from 52. Not those, not the threes. You have 4 cards from 51 then. Yeah. Does that make any difference? It works out the sum of these two. Okay, if you think 0, the one that we had before 0 is silly. Okay, if there's only one winning card, working out the first term would be silly. But just suppose you have 4 winning cards instead of 3. Adding these two together, what do you have? You will still get 51 times 52. I don't have a calculator, so I'll keep them on the bottom line. I've got a 4 here, so that I have a 3 plus 51. So 3 plus 48, sorry. 48, which is 51. 4/52, exactly the same as this again that we had. Okay? So imagine that you're in any of these lucky draw and that sort of where you have to pick a card or ticket from a pile, and then you are not sure whether going first or second would increase the chance. It wouldn't. Okay, in principle, it wouldn't. It wouldn't change at all whether you go first or go second. But of course, in reality, okay, in reality, especially when you have to pay to play this game, if you have to pay to play this sort of game, then you will have to. Then what you would do is, I don't know, wait. After all, you will wait to see if your friend got the winning card first. Because if he does get the winning card, then of course it really will reduce your chance of picking another winning card. Okay, of course you will, and of course if a friend doesn't tell you what he's got, okay, if your friend doesn't tell you what he's got, then the things will be different. Okay, well, the probability would be the same, but assume that this friend of yours pick out a card and then he show you that he's winning, he's won or he has not won. Then it will change the probability of your winning. So especially if you're paying for these things, after all, you are not forced to play anyway. If you are forced to play anyway, then maybe it wouldn't matter again. But if you're not forced to play, then why don't you just wait for your friend and see if he gets the winning card, then you will just walk away, because it has reduced your chance of winning. Okay, otherwise, yeah, you can join if your friend loses. Yeah, so a little gaming example here that we can apply our total probabilities. Okay, but today we're going to show you the other, just as important, the Bayes theorem. The other concept here, the Bayes theorem. Okay, very important. It allows you to connect the probabilities of B given A with the probability of A given B. It's really just an extra step from our total probability, using the concept, using the proper definition of probability of B K given A is simply given by the probability of BK intersect A divided by the probability of A. And the top line can be written as this, the probability of A given BK times probability of BK. But the bottom line is your total probability here. Okay, very important theorem here connecting these two conditional probabilities. Let me give you an example. Suppose that, okay, someone wishes to, well, have a pet, okay, a cat for, but you see that people who are people who are allergic to cats, okay, the furs and all that, okay, cats, dogs, or birds, I don't know, okay, some people are allergic to that sort of things, okay. So before they decide to have a pet, they may decide to they may go to a hospital or whatever clinic to test if they have the allergy there. Okay, so they have to do some kind of medical test. I don't know what that is like, but these things. But what I do know is whatever medical test that you're having, or whatever test that you're having in reality, they're not always accurate. That means what? That means if you have the allergy, they will probably say yes, telling you that yes, you do have the allergy. But it is possible that if you do have the allergy, it may say no. It may give you a negative result. Okay, if you do have the allergy, it says negative. Okay, it's not accurate, so there might be errors, and you may get some result like this, or what we call a false positive. Sorry, false negative. It tells you that you got a negative result when you don't have the allergy. When you do have the allergy, sorry. And on the other hand, if you don't have the allergy, it is still possible that you will get a positive result. Yes, sometimes. Okay. Then what? Then suppose that well, after all, that not many people are getting not many people are having allergies after all. So suppose only 1% of the population will have this allergy. And of course, I'm making numbers up. 1% is a lot. 1% is a lot. Compared to a city with millions of people, 1% is a lot of people. So don't worry about these numbers. I'm just making things up. Suppose that there's only 1% of the population having the allergy. And the test gives a positive, and it gives a positive test result. The test says yes to someone who has the test. Okay. If someone walked into a hospital or a clinic and having one of these tests done, and then it says positive, what are the chances? What's the chance that he or she actually has the allergy? You see, having the allergy or not is not quite the same as getting a positive or negative result from these medical tests. Okay, so for ordinary people like us, we only care. We only want to know if we're getting a positive result or negative results. What is the actual probabilities that we're having the whatever disease or allergy here? While the accuracy of these tests, the accuracy is defined as if for people with allergy, how the probability of this giving you the true answer, giving you the right answer here. Okay, that's what is defined as the accuracy here. If people do have the allergy, it says yes, it says positive 80% of the time. So it's not, it's kind of okay, not very accurate, but okay. Okay, that is to say, what we're looking for is, okay, what have I got here? Allergy, and then yes. Okay, so we have yes, the probability. So we are looking for the probability of having allergy. Given that it says yes, given that it says positive, Okay, this is what we're looking for. But what we do know is if you have the allergy, there's only 80% of the chance of giving you a positive result. Okay, on the other hand, you still get 10% of the probability of getting a positive result if you don't have the allergy, what we call the false positive. False positive. Okay, that's what we have. Okay, and we're looking for this one here. So what do we do? And this 1% here is what we call the probability of people getting allergy after all. What does that mean to us? Well, my my base theorem tells us that what we're looking for, the allergy, or a given that it is positive, is given by this expression. It's given by this expression. On the top line, okay, you need to have the allergy, and then the test says yes to you. On the bottom line is simply having a positive result. Then what we have here is, if you in order to get a positive result, you either have the allergy and then it says yes, or you don't have the allergy and it still says yes. So we just need to pop all the numbers into the formula, into the equation. Then we have all we need. Sorry, so I should repeat here. People having allergies 1%, so 0.1 here. That means you're not having allergies, like 0.99, 99% of the chance you're not getting allergy anyway. But when you do have the allergy, you have got 80% of getting the positive result. If you don't have allergies, you get 10% of getting this guy. So this probability of having a positive result is simply what? What's that equal to? 0.008, 0.008 plus 0.099 equals 0.107, something like this. This is 0.107 on the bottom line, but on the top line, you've only got things like 0.008, something like that. Have I? Yeah. And my calculator tells me that this gives me a 0.075, something like this. So it's like 7.5%. 7.5%. Is that a lot? Is that a lot? Is that a high? Is that a high probability here? 7.5%. If you have a positive result from a medical test, it's 7.5% of the chance that you do actually have the allergy. That's not a lot, is it? That is not a lot, is it? Okay. Normally, you would believe these medical tests, and if it says yes, you think that you're having the disease or whatever. But now it tells you that you only got a 7.5% after all. Not a lot. Okay. Not that you should. I mean, it's of course a lot higher than 1% here. Okay, a lot higher than 1% here, but it's still relatively low, 7.5%. What does that mean? Think about the COVID-19 these days. I don't know how. Have you done a lot of these testings before? Yes, since what? It's been a year and a half, more, almost 2 years from now. okay, our COVID-19 thing here is developed. Or I don't probably you have done some of these tests before in a whatever institute or hospital and all that. So they kind of check your throat or whatever. They get some samples from these, and then they check whether you have these sort of viruses. Yeah. But again, these tests they're not always accurate. Just like at the beginning of this pandemic, they develop these tests. They have arguments about the accuracy of these tests. Okay, when you have so these accuracy of tests, they're about these numbers. If people have the disease, how much times or how much of these times or how likely it will give you a positive result, and if you don't have the disease, how likely is it it's a test to give you a negative result. Okay, but just as always, we're going to have disease or no disease, and positive, negative. Okay, you get results either positive, that means you have the disease. Well, now you know they're not necessarily the same thing, or negative, that you don't have it. So you're hoping these two happen. If you have the disease, it gives you positive. If you don't have the disease, it says negative. You're hoping to see these two outcomes, but you know that there are always these two, which we call false positive, and we have the false negative. Okay, and you know that, and you should know by now, after all these years, after all these 2 years, you probably know that you heard of these. You would have heard of these terms a lot: false positive, false negative, and which one is more dangerous? If you get a false positive, that means you don't have the disease, but it just gives you a positive result. Then yes, you'll be scared, but there's no harm to the community. You'll just get separated, and then have your quarantine, etc., 14 days or 28 days, etc. But if you have given false negative result, you have the disease, and then it tells you negative. They will just send you out there, walk around in the city, and then people may get infected and all that. So the false negative is actually more of the problem. Yeah. But you have to understand that these two, they might occur. Well, but we're hoping these two probabilities will be small. Okay. But as I say, for ordinary people, we want to know that if we get positive result, what is the probability that I do have the disease? This is what we care. In fact, this accuracy thing is done the other way around. So we will have to do these calculations to see what we actually have. Okay? But it turns out mathematically we can show that if you have a positive result somehow, it doesn't necessarily mean that you've got a high probability, you've got a lot of chance to catching the disease. Strange. I've got a strange feeling. Something wrong with these medical tests, isn't it? I've got another example here, which I have to admit that these PowerPoints were written earlier, before COVID-19. So if I knew that, I should change that PowerPoint to actual COVID-19 example here. But suppose that I've got whatever values, again, the accuracy. Think of them as 90. This time is a lot more accurate. Okay, 90%. If you have the disease, whatever that is, whether it's breast cancer or COVID-19, whatever you can put in. No worries. It's the same thing, same calculations. Really, it's suppose that you've got the accuracy of 90, so that if you have the disease, 90% of the chances to give you a positive. But on the other hand, you still get false positives. 8% of the chance you'll get false positive. You don't have the disease, it tells you positive. Okay, suppose that this disease, okay, I don't know the figure for COVID-19. Well, of course it depends on country and depends on, from time to time it's different. Suppose only a certain small value for of the proportion of the population would get the disease. Okay, again, 0.5% is not necessarily small proportion, but let us assume that we have this number. Okay, what does that mean? If you do get a positive result, what does that mean to you? A similar calculation, just like the one we had for cat allergy, it works out similar value here. I've got a 5%. Okay, is 5% a lot? Well, it's not a lot. For an ordinary people like us, for ordinary people who don't do statistics, who don't know probabilities or statistics, they probably would scare to death if you get a positive result from whatever medical test here. But especially if it's like COVID-19, that sort of deadly virus here. If you get a positive result, you probably will scare to death. But in fact, the math tells you that it's not exactly that likely. Okay, not exactly very likely that you will have the disease. Okay, but then you would question, but then as an ordinary people, okay, again, you would question, what's the point of these medical tests after all? Are they just some kind of scientific ripoff? Okay, just the people trying to get research funding money just from the government or from the whatever things here. They develop all these things just to fool people. They say there's a test. They say it's just so accurate, but they say, oh, a joke, so that because I'm getting a small, very small probability of having the disease even when I have a positive result. What's the point of all these things? Okay, something not in our understanding of the society or whatever, or of everyday life. Yeah. As it turns out, okay, as we said earlier, the problem about these medical changes, well, or whatever diseases, is not from the false positive. If you get a false positive, they just lock you up for quarantine 14 days, no problem. Okay, you'll be the one to start suffer, of course. Yeah, we have to admit that. But having the false negative is dangerous. Let's have a look. The point of these medical tests is actually this: if you don't have the disease, well, if you have a negative result, if the result says negative, if the result tells you that you don't have the disease, the probability that you actually have the disease can be done in a similar way, of course. Okay, can be done in a similar way. You either have the disease or not have the, but you either get a positive or get a negative. You see, you can work out these probabilities in exactly the same way. You've got all the numbers already. What is this? 99.95%. You're most likely safe if you have a negative result. So now you understand what these tests are all about. They are not trying to identify people with the disease. They are trying to find out the people who don't have the disease. Okay? They're trying to find the people who don't have disease to assure, okay, if you get a negative result, you're probably okay. You're most likely to be okay. Okay? Understand? Yeah. So if you touch wood, if you went to one of these medical tests and then it gives you a positive result, what do you do then? What do you do then? Okay, if it says negative, okay, the whole point about this is find out the one without the disease. If you get negative, you're good. Okay, but if it says positive, after all, again, this is what we care. If you do get a positive result, what do you do? Or what do people do in the hospital? What do you know? What's your experience? They would ask you to test again. Again, this is not something that, not exactly something that a rip off. Again, I've seen you keep paying for doing these medical tests. If you get one and then it says positive, and then you don't believe it, and just and they ask you to do it again. Again, if you get a COVID-19 positive result, they wouldn't just leave you alone there. They would just have you separated from the rest, and then they would just keep doing other tests on you to see if you really have the disease. Yeah, so they would just keep on doing these tests to you here. So because yes, if you don't have the disease, if you get a positive result, it is unlikely that if you get a positive result, it is still unlikely that you have the disease. But if you get more than one positive result, okay, if you repeat this tests and then you still get positive results, then you're getting more and more likely to actually have the disease. These probabilities would increase if you repeat this process. Okay. The whole thing is, of course, you just keep doing these tests. If just one of them gives you a negative result, you're probably okay. But if you keep getting positive results, then you know that the chance of you actually having the disease is getting higher and higher. Don't worry too much about these calculations. It's based on a lot of these assumptions. Okay, so it's not necessarily true, but it's just roughly speaking something like this. If you have the disease, okay, if you have the disease here, the chance of having two positive results, okay, and therefore, similarly, if you have two positive results, what's the chance that you're actually having the disease? It's getting higher and higher, as you would expect. Okay, so then normally when you have done any of these medical tests, it gives you something not quite normal. Okay, I would say definitely a disease or something that was not quite normal. They will ask you to repeat this, do it again, see what happens. Again, it's not something that to ask you to keep paying money and all that. Okay, it's just something for safety, really. Do it one more time or do it 3 times, etc. See if you actually do have it. Of course, if you are for COVID-19 case or whatever in real life, then they will just give you other tests, not quite the same tests, something more accurate or different tests to see if you may have the thing. Okay, but I mean, just the identical, the same test will be just as helpful. Yeah. I hope that makes sense. That's something that we can do, apply in reality with our total probability and Bayes theorem. Okay. So let's just stop here for a moment and then we can move on to the next bit here.